Hello my friends and welcome to this new step of the training implementation. We just initialized the hyperparameters and now we're about to pre-process the frame. So now, before we start, I want to highlight something very important. Remember, in the previous implementation of deep Q-learning, the step after initializing the hyperparameters was to implement experience replay. Although now we won't do the same for our implementation of deep convolutional Q-learning simply because now the input states are no longer input vectors of a small size, they are now input images of a big size because there are many more dimensions. So you can imagine that unless our AI has a super powerful memory, well, we can't store 100,000 experiences containing all these images in the memory of our AI. And therefore, that's exactly why we have to not only make a simpler implementation of experience replay, we will still have experience replay implemented in the DCQN class, but most importantly, we have to pre-process the frames so that the input images can be converted into PyTorch tensors that are accepted by the neural network of our AI, meaning first the eyes represented by the convolutional layers, and then the brain, the artificial neurons represented by the fully connected layers. So that's exactly why we're not implementing experience replay, but most importantly, we are pre-processing the frames so that they can be fed into the neural network of our AI. Alright, that's what I wanted to highlight. Now there we go. Let's do this. Let's implement this new code cell. So first of all, we're going to import a new class which is called image and which is taken from the PIL library, which is the Python imaging library, and which will allow us to load images from files and create new images. Okay, so we will basically need that for the image preprocessing. And so here we go. We start from PIL, the PIL library, from which we import the image class. Great. Then we will also need the transforms module from the Torch Vision library, and therefore I'm going to start from the Torch Vision library, from which I'm going to import this transforms module. And now there we go, we can implement this new function. So we're going to call it preprocess underscore frame, which will take as input, according to you, what exactly? Well, of course, the frame, right? The frame meaning the real frame coming from the game of Pac-Man, which then will be converted into PyTorch tensors, of course. Okay, so here we go. That's the only argument it has to take. And now let's define what this function has to do. All right, so right now we have a frame, right? The frame of the game, one frame of the Pac-Man game at a particular time. But in what form is this frame? It is in the form of a NumPy array, which represents exactly the image. And so the first step we have to do here is to convert this NumPy array, which is our frame, into a PIL image object, because we will need that for the next steps of the image preprocessing. All right, so how we're going to do this? Well, first we're going to update our frame. Right now it is a NumPy array and we want it to be a PIL image object. And so to convert this into a PIL image object, we're going to use our image class, from which we're going to call the fromArray method. All right, which will take as, of course, our frame now in the form of a NumPy array. All right, perfect. So now our frame here becomes a PIL image object, which is exactly what we need for our next step. And so now what is the next step? Well, now is the time to do the main preprocessing, the preprocessing that will lead to that PyTorch tensor that our neural network expects, the neural network of our AI. And so what we're going to do now is create an object which will be a pre-processing object. Basically, it is an object that will pre-process our frames, but in the format of our PIL image object that we just got thanks to the fromArray method. And so there we go. Let's define this new preprocess object, which will be created as an instance of the compose class. And this compose class is taken from the transforms module, which we just imported from the Torch Vision library. And so there we go. From this transforms module, we're going to call the compose class, which will take as input only one argument here that we absolutely have to input, which is a list, which is why I'm entering a pair of square brackets here, a list that will contain the different transformations we're going to do through our preprocess object. Okay, so what is going to be the first transformation is going to be a resize of our frames, because indeed, remember that the frames will have this dimension. We can actually also see it, remember, in the setting up the environment code cell. This is the original dimensions of our frames, 210 by 160 by 3, corresponding to the 3 RGB channels for colored images. But there you go, these are the original dimensions, and actually, if we keep those dimensions, we will have a very difficult training. We not only need to lower the dimensions, but also make squares, which is why we're going to have, after the image preprocessing, dimensions of 128 by 128. And that's, of course, for the convolutions that we applied to our preprocessed images. Here with the first convolution, we have the 32 filters here which filter the preprocessed framed converted into torch tensors while applying the convolutions, and therefore having dimensions of 128 by 128 will make it easier than having those dimensions, and that's exactly why here the first step of this transformation we have to input in the compose class is to indeed resize into 128 by 128. And be careful, here I included two parentheses because actually these are the dimensions entered into a pair, which is the argument of the resize class. And by the way, this resize class has to be called from the transforms module again, which we imported here from the Torch Vision library. Okay, so that's the first transformation, and now we have to enter the second one, which is of course the conversion into a PyTorch tensor. And so how we're going to do that? Well, first we're going to call our transforms module again, from which we're going to call this time the toTensor class. And this will exactly make the second part of the image preprocessing, which is to convert our pill object frames, first resized into 128 by 128 dimensions, and then converted into a PyTorch tensor. Okay? And you also have to know that this transformation will also normalize the frames, meaning that this will also scale the pixel values to the range between 0 and 1. Alright? And now, well, we just have one final step to do, which is to return the preprocessed frames. And to do so, well, we're going to call our preprocessed object, of course, which will take as input, of course, our frame pill image objects. Perfect. And now, according to you, are we done? Well, almost. Remember this very important thing we have to do most of the time in deep reinforcement learning. Let's never forget that extra dimension of the batch. Remember that our frames always need to be in their corresponding batch, and in order to keep track of which batch each frame belongs to, well, we need to add this extra dimension of the batch, and you know how to do this. We did it many times already in the previous implementation. Of course, we're going to use the unsqueeze method, which will just take as input one argument, which is the index of that dimension of the batch, and usually we set that as the first dimension. And so we're going to enter 0 so that the dimension of the batch will be the first dimension. Alright, and we're done with the preprocessed frame function. So now we're going to integrate that function, of course, in the DCQN class, which we will be implementing in the next tutorial. So there you go. That's exactly our next step here, implementing the DCQN class while integrating experience replay and image preprocessing. Let's get some good energy to do this. And as soon as you're ready, well, join me in the next tutorial to smash our DCQN class. And until then, enjoy AI. Hello my friends, and welcome to this new step of the training implementation, that very exciting step, implementing the DCQN class. And the good news for us right now is that it's going to be almost the same as the DQN class we implemented before for our deep Q-learning model. So of course, as efficient AI scientists, we're going to select this whole code, copy it, and we're going to paste it in a new code cell of our deep convolutional Q-learning implementation. There we go. And now let's do the little changes to adapt this to our deep convolutional Q-learning model. So of course, what I'm going to do first is zoom out a bit because the code cell is huge. But of course, in the comments, feel free to let me know if it's too small. I just want us to be able to see the whole code so that we can, manage those changes more easily. So let's do it one more time. I hope it's going to be okay. Okay, I think that's enough. I'll do some scroll up and scroll down, but let me know if the zoom out is too strong, okay? So, first of all, what is the first very easy update that we have to do here for our deep convolutional Q-learning model? I'll give you a hint. This is exactly where the cursor is right now. Of course, what I'm talking about is the soft update. Indeed, as said before, we're not going to do any soft update for our deep convolutional Q-learning model for Pac-Man because indeed, I experimented this before. It doesn't really improve the training results. So let's remove this. And what is the next thing we have to do? Well, it's the same hint. It's again where my cursor is. of course, we have to remove this row in the learn method that indeed calls a soft update method to perform the soft update. So let's remove this, and there we go. Okay, good changes done. Now, what according to you is the next step? Well, maybe now is the time to check for those changes from the top. Alright, so let's do this method by method. We're gonna change the little things to adapt this to our deep convolutional Q-learning model, and let's start with the init method. Alright, so first, do we have to change anything in the arguments here? Well, yes, of course. For our new use case, training an AI to play Pac-Man, well, the state size doesn't make much sense, so we're going to remove it. Not only it doesn't make much sense here because of the images input, but also we won't use it. So we remove it, and also, let's not forget that, let's also remove it in the network class, because indeed, the network class no longer takes as input the state size. So I'm removing it here as well. Here we go. Done. Perfect. So good first change done in the init method. Now, what is the next obvious change we have to make? Well, this one, of course. Remember, previously in our deep Q-learning implementation, the self state size was indeed an object variable of our agent class, but not anymore for the same reason we just mentioned. So let's remove it as well. And now, what is the next obvious change? Well, of course, it has to do with the memory. But be careful, we still want to implement experience replay. So the only thing we're going to do here is just remove the replay memory class because we haven't implemented it in this new deep convolutional Q-learning implementation. So let's remove it, and instead we're going to replace it with a simple double-ended Q, which remember we get thanks to the deca function, and which takes as argument the capacity, but the name of the argument is actually max len. Okay, and so far we're going to set that to 10,000. Okay. Alright, and now, is there one more or one final thing we need to change? Well, yes, but that you can't really know. It's because actually what we did here in the step method of our deep Q-learning agent previously, sampling the experiences and learning every 4 steps, well, we're no longer going to do it for our deep convolutional Q-learning agent. And that's because, we are making a simplified version of experience replay, which doesn't use this. So, we're not going to use self.tstep object variable, so we're going to remove this, and now we're done with our init method. Okay? So, since we just removed self.tstep, well, let's also remove it here because we won't use it. So let's do this here and here as well. Okay? So now we completely got rid of self.tstep. And now, according to you, what do we need to change in our step method? Well, it's pretty obvious again. Push here is a method of the replay memory class, but since we haven't implemented it for the deep convolutional Q-learning model, well, of course, we're not going to use it here. So I'm going to remove this line of code, and now let's see what else we have to update here in the step method. Alright, so first let me just fix the alignment here super quickly, so I just have to do it like that. Same for here and this, and all good. So now, what do we have to change here in this step method? Well, remember what we just removed. We just removed that push method that indeed appended an experience into the memory. And so, what we need to do is actually replace this append through the push method by a simple append. And, well, for that we have the append function. So, that's exactly what we're going to do now in this step method. But before we do this, according to you, what do we have to do? Basically, now we want to append this whole new experience here in the memory, just like we did before in the step method of our deep Q-learning agent. And so, well, we have everything to append to the memory, but the state and the next state are not pre-processed yet. And in fact, in the memory, they should be already pre-processed because then they will be fed into the neural network. And so the simple thing we have to do here to start with in the step method is just to pre-process the state and the next state, which so far are NumPy arrays because they're coming from the images of the game. And so we just want to pre-process them to make them ready to be first added into the AI's memory and then fed into the neural network. So let's do this. Let's first update the state. And to do this, we're going to call, of course, our preprocess frame function, which will take as input what? Well, of course, our state, but so far in the form of a NumPy array. So here it will be a NumPy array, and then it will be a PyTorch tensor that is, remember, resized and normalized. All right, so that's done for the state. Now let's do the same for the next state. And so, well, let's just add here next underscore and here next underscore, and done. The next state is now pre-processed. Perfect. So now what can we do? Well, we can append this whole new experience of the pre-process state, action reward, pre-process next state, and done into the memory. So let's do this. Let's call our memory object, not coming from the replay memory class, but simply created as a double-ended queue. And then, well, since it's a double-ended queue, we can call the append function, the classic append function, to append what? Well, the tuple of all this, the whole experience composed of the pre-process state, the action, the reward, the pre-process next state, and done. Alright, so I'm copying all this, I'm pasting that into that tuple of the experience, and now we're done adding this new experience to the memory. Alright, so now let's check the end. Are we all good here with those last 3 lines of code of our step method? Well, there is a little issue here. Can you see it? Well, I'm going to tell you it has to do with this. You notice this self.memory.memory? Remember, we had this before because previously the memory was first created as an object of the replay memory class, and this was exactly the object. But then we also had the memory attribute. But now our self.memory is not created as an instance of the replay memory class, and therefore it doesn't have a memory attribute. So we just need to remove the memory attribute here and only keep our self.memory object variable. Okay, so we're all good here. And now, according to you, do we have to change that line of code? Well, yes, of course, because again, previously we implemented this sample method, in the replay memory class of our deep Q-learning implementation, but now we no longer have the replay memory class. And so, how can we replace this by a simple sample function that will sample some experiences from the memory? Well, by simply calling the sample function from the random library, which we imported before. So that's exactly what we're going to do. I'm going to actually take all this self.memory and simply replace this by random. Okay, great. So basically we're calling the sample function from the random library, which will take what as input? Not directly 100, but first it has to take our memory, self.memory, because we have to sample from the memory. And then it will also take the number of elements we want to sample, which is of course our mini batch size, which was a variable we initialized before. And therefore let's do this. Let's enter that other argument, which is k here, and which is equal to mini batch size. Alright, and now finally, do we have to change anything in that last row, self.learn experiences discount factor? Well, good news, no we don't, because we'll still use that learn method to update the parameters of the model when we call the step method at each step of the training. So basically we're done. We have successfully adapted the init method and the step method for our new agent class of the deep convolutional Q-learning model. And so now we're going to do a little guessing game, but only with one question. The question I have for you is, do you think we have to change anything inside this act method? Alright, that's the question. I'll give you the answer in the next tutorial, and we'll see in the next tutorial if we have to change anything in the act method or if we can directly update and adapt the learn method for our deep convolutional Q-learning model. So think about this, and we'll do what's necessary in the next tutorial. And until then, enjoy AI. Hello my friends, and welcome back to the implementation of our DCQN class. In the previous tutorial we adapted the constructor init method and the step method, and by the end of it I asked you a question, which was, do you think we need to change anything in the act method in order to adapt it once again to our new DCQN agent class as opposed to the previous DQN agent class? And the answer to the question was yes, we had to make one single change, which had to do of course with the state, because indeed here previously we applied the torch.fromNumPy function to convert the state into a torch tensor, because the state was an input vector of one dimension. So this was a perfect fit. But now our input states are input images, and therefore we can no longer use this torch.fromNumPy function. And so how do we need to change this? Well, that's of course thanks to our preprocess frame function we defined before instead of experience replay. So let's do this. And besides, the good news is that in the preprocess frame function we already included the unsqueeze, to add this extra dimension of the batch. So we won't have to do it again. However, we haven't included this to send this to the proper device, and so we will keep this. Therefore, the only thing we have to do now is just take all this, torch from NumPy up to unsqueeze, and then just replace this by preprocess underscore frame function, which will take, of course, as argument, the state. And there we go. That was the only change we had to do. We just needed to pre-process the state the right way, because now the state is not an input vector, it is an input image, but of course in the form of a NumPy array. Alright? So great, that was the only change, and now let's do the final change in the learn method. So here we have a little more to do. According to you, what it is exactly that we have to do. It's very important to not forget this. Well, I'm going to tell you, remember that in these formula, computing the Q targets, the next Q targets, and the expected Q values, well, we do this on stacks of states, and stacks of actions, and stacks of next states, okay? And so, if you notice, since we haven't implemented the replay memory class, well, we don't have those stacks of states, stacks of next states, etc. And so that's exactly what we need to do here. We need to get the stacks of states, the stacks of next states, the actions, the rewards, and dones, so that we can compute these formulas on these stacks. Alright? So the first thing we're going to do here, because we already have the experiences, that is an input of the learn method, the first thing we need to do here is to unzip our experiences, meaning to separate the different elements of the experiences, states, next states, actions, rewards, and dones, separately. Okay? And how we're going to do this? Well, we're simply going to use the zip function, which will take, of course, the experiences as arguments, but we're just going to add a little star here in front of the experiences. As you can see, it is what is expected for the iterables here in the zip function. So we just have to add this little star, and then this will unzip those experiences into the states, next states, actions, rewards, and dones. And now we can do the stack. And so now it's going to be funny. According to you, how can we do this stack? Well, it's very important to notice that actually right now the states and next states are already PyTorch tensors, because indeed the states and next states come from the experiences, and the experiences come from the sampling from the memory. And to the memory we just appended the state, action, reward, the next state, and done, and the state and the next state here were already pre-processed with our pre-processed frame function. Therefore, they're already PyTorch tensors. So at this point, the states and the next states are actually PyTorch tensors. So, a priori, we would think that we couldn't use, again, that vstack function we used when we implemented experience replay. Remember, here we used this vstack function to perform the stacking. But the vstack function is actually a function by the NumPy library, which therefore we would think would apply only to NumPy arrays. But here's the good news. Actually, the vstack function can actually take as input a tensor, like a PyTorch tensor, and automatically convert that into a NumPy array so that it can perform the stacking. And therefore, we can still call the vstack function here on our tensors, I'm talking about the states and the next states, to perform the stacking. And then we'll still use this torch.fromNumPy function in order to reconvert that into PyTorch tensors. Alright, so that's the easiest way to do it, because we already have the code. We're going to take exactly this. The other alternative that we could have done is to use the torch.cat function by the torch library, meaning the cat function for, concatenate by the torch library. But we already have this, so let's just take this. And so here I'm just going to copy these 5 lines of code, all of them, because it's going to be exactly the same. And then back into our deep convolutional Q-learning implementation, I'm simply going to paste this. Alright, and now, new guessing game. What are the very final things we have to change in this new agent class of our deep convolutional Q-learning model? These are only 2 things. Let's start with the first obvious one. It is the order here. We have to respect the order of the experience, starting with the states, then the actions, then rewards, then next states, and dones. So I'm just gonna take that next states here, cut this, and then here I'm just going to paste it. Alright, so now the order is respected. That was the first change we had to do, and now, what is the very final change we have to do in order to adapt this learn method to our deep convolutional Q-learning agent? Well, I'll give you a hint. The answer is in the vstack function. Well, the only thing we have to do is, of course, to replace these for loops here by simply the element. So we remove that whole for loop in a list, and here we replace that, of course, by states. Alright, and then, well, let's do the same for the other ones. We remove that whole for loop in the list here, and we replace that by actions. Alright, there we go. Then we remove that whole for loop in this other list here, and we replace that by rewards. Okay, and then 2 more to go. We replace that whole for loop in the list here, and we replace that by next state. And finally, the very final change of this learn method, we remove that whole for loop in the list here, and we replace that by done. And there you go, my friends. Double congrats, because not only we're done with our new learn method adapted to our deep convolutional Q-learning agent, but also we are done with our new agent class. There it is. We have a complete view at it. Here is our new agent class for our deep convolutional Q-learning model. So huge congrats. We did this successfully and efficiently. So now we basically have the model on how to create a deep convolutional Q-learning AI agent. But remember that we still don't have it for real. And that's exactly going to be our next step. Remember, once the class is defined, we can now initialize our DCQN agent by creating an instance of that agent class and therefore get that AI for real. So we're going to do that in the next tutorial. But first, let me just run the previous cells that I haven't run so far. I think I left things at, there we go, initializing the hyperparameters. Let me just run this cell to initialize the hyperparameters, then run this cell to pre-process the frames, and then finally run this cell to define the agent class, which will allow us to build our future deep convolutional Q-learning AI model. I can't wait to do that with you in the next tutorial, and until then, enjoy AI.